Okay, here we are back in my little eVTOL again, and let's just do bodies. It's a pretty straightforward one. For each body in the airplane, have as many as you want, up to like 45 or whatever that is, and check the little box if you've got it. Okay, then you enter the number of stations, which is the number of these little stations you're going to enter your radius for, and then the number of radii per side. That's the number of little radial points here around the side to define your shape. Your grid radius, that's like the radius for the body cross section. The area rule ratio. So if you enter 1 for the area rule ratio, then that means by the time you go up to supersonic speed, your body has gone completely to that high drag supersonic model. But what some airplanes do is as where the wings or the tails or the engine pylons come out of the body, they kind of neck the body in to make the body thinner. And what that does is it gives the air a place to go. As the air gets out of the way of the wing or the engine pylon or the engine nacelle, it can get out of the way by going into that kind of recessed area in the body of the airplane. In other words, the airplane holds a constant cross-sectional area from nose to tail as much as possible, especially near the middle. And that's what lets the air get out of the way of the wings and tail and whatnot at speeds approaching the speed of sound. And if you look at some business jets, and I think this includes the Citation 10, you'll see that the tail, the body of the tail itself really necks in and gets narrow. And it's kind of like, it's like somebody carved something out of the body near the engines. And that's so that as the air goes around the engine pylons and out of the way the engine nacelles, it has a place to go. In this case, into that necked in part of the body. So if your area rule ratio is 1, that means you did not do that at all. And you go completely to the supersonic drag model as you approach the speed of sound. But if you enter a value a little less than 1, then what that's saying is, oh, you don't have all that supersonic drag. We avoid some of that supersonic drag approaching the speed of sound with area ruling. And so you can enter this value as necessary. I doubt you'd ever enter more than 1, but you can enter this value as necessary to hit your transonic performance in your particular airplane. Then we got our body coefficient drag, 0.135. Notice I said possible CD if there's a streamlined body is 0.044 based on wetted area fineness ratio and estimated cruise Reynolds number. So in other words, I guessed with an algorithm that the coefficient of drag might be 0.044, but you'll notice that what I actually entered is 0.135. Why did I enter a value 3 times my estimate? And the answer to the question is, my estimate is based on the most streamlined teardrop shape you could ever imagine, okay? You have this, imagine you have a total streamlined teardrop, long, thin body shape, lowest possible drag you could ever imagine, like the drop tank of a fighter jet, right? Just the most smooth, streamlined shape ever. Well then, yeah, the coefficient drag might be 0.044. But by the time you make this body like kind of square, so there's room for people in there, and then you have like wings and landing gear and stabilizers all coming out of it, and really a non-optimal aerodynamic shape simply to hook up to the things that make an airplane usable and to carry the stuff that make an airplane worth having. You've got at that point, I found the coefficient drag that is way, way worse than your optimal ideal. So the optimal ideal coefficient drag might be 0.044, but I found in practice you should enter 2 or 3 times that. Maybe twice that if you have a nice streamlined jet, and 3 times that if you have a less streamlined propeller airplane. We can copy geometry, or we can attach an engine. Here, let's go to this one. This is the nacelle for an engine, and so you'll notice I attached it to engine 1 as a nacelle. We can also attach to landing gear. Oh, I probably did that here. Here we go. Attach to landing gear for your wheel pants. You see? So you got your wheel pants attached to your landing gear. You got your nacelles attached to your engine, and your body not attached to anything. And then your arms and offsets to simply move the bodies around or aim them around. And then the textures, which I'm really not going to fully explain other than to say that's the way we used to texture airplanes before we made bodies or object files to really make the airplane look right. And this body texture thing will be deleted at some point because it makes your airplane look like you built it in 1990 on an Atari. So we're not going to keep doing that. But, why don't we take a look? This is kind of important. The top view, you see you got the top view of the body, and then you can drag, nodes around. And then if you accidentally get it out of the way you don't like that, you can just go, poop, reset it to vertical. And that way you can, kind of change the shape, but keep them all in nice straight sections. Then the side view, same as always, drag them around. Oh, and whenever you drag the top one. In the side view, watch. That is where you set the longitudinal station of each section. So go into side view, drag the top one around, and hit reset all sections to vertical. That's how you decide where longitudinally the pieces are. Boy, I hope I remember to not save this airplane when I'm done with this demo. And then your bottom view, which is now messed up by my obvious work just now. And then the front and back looks like a Spider-Man web somehow, but there's a front and back view of the airplane as well. So that is how we do the bodies of airplanes.